Hello friends, nucleophilic substitution in pyrrole, furan and thiophene. We have seen that the reactivity of pyrrole, furan and thiophene towards electrophilic substitution is in the following order. ये order है pyrrole, furan and thiophene. Now the reactivity of these rings toward nucleophilic substitution is in the opposite order. So just remember electrophilic substitutions order. Now pyrrole's ring is the least reactive and both 2 halo and 3 halopyrroles behave like aryl halides in nucleophilic displacement. You know, 2 chloropyrroles does not react with the potassium tert-butoxide or with lithium aluminum hydride. No reactions. Now, furan are more reactive towards nucleophilic displacement than pyrrole. 2-bromo and 2-chloro react with piperidine at 200 degrees Celsius as follows. You can see the nucleophile approaches this carbon and forming a 4 bond, and then you can see the products. The presence of electron withdrawing group. Here, important is electron withdrawing group on the furan ring facilitate nucleophilic displacement. Thus, 2-bromo 5-nitrofuran and methyl 2-bromo 5-carboxylate react readily with nucleophile. You can see the reactions. So, it is of considerable interest that in this reaction the furan react about 10 times faster than the corresponding benzene analog, and this strong behavior has also been observed in thiophene series. So thiophene nucleophilic substitution occurs much more readily within the thiophene series than it does for the corresponding benzene compound. The thiophene are at least 1000 times more reactive than corresponding benzene analogs, and this increased reactivity has also been noticed in the electrophilic substitution of thiophenes compared to corresponding benzene analogs. You know, my friend, the increased reactivity of thiophene ring nucleophilic substitution can be explained by Wieland intermediates involved in the nucleophilic substitution of bromine in 2-bromo 5-nitrothiophene. So you can see the reactions starting from the thiophene nucleophile, the formations of nucleophile with the carbon bond, and that one is the resonance stabilized. It is suggested that the sulfur atom causes additional stabilization by involvement of its d orbital structure. So it must be noted that the ion pair of the sulfur atom also enters into resonance with the pi electrons. X-ray studies indicate that the valency angles of CSC in thiophene is nearly 91 degree and not 105 degree as expected, and this can be explained by assuming that the 3d orbital of sulfur are also used in resonance, and following additional contribution structure may be written as you can see the resonance. So copper mediated nucleophilic substitution of halothiophene are also of great synthetic utility. Example of some transformations below. You can see I converted into YNE, I converted into CN, and I converted into bromine converted into SBU with the help of copper acetylide, copper cyanide, or copper S-butyl in presence of quinoline. Now the reactions of furan, you can see the chlorination, bromination, nitrations, sulfonations, and acylations. Reactions of thiophene, you can see iodinations and brominations, nitrations, sulfonations, and acylation. Reactions of pherols, you can see the halogenations, nitrations, sulfonations, azo compound formations, reactions on nitrogens, reactions on add-to positions. So acidic character of pherol is due to pherol is resonance hybrid of various structure carrying a positive charge on nitrogen. The greater stability of the pherol anion compared to pherol, you can see. So the higher stability of the anion is due to the resonance. Now the acidic character is also reflected in the formation of pherolyl magnesium halides when reacted with the alkyl magnesium halides. You can see the reactions is going. The action of acid pherols, thiophene, and furan. You can see. Now the mechanism of trimerizations of pherol and in acidic media. You can see the reactions.